Now let's practice what we just learned in one example. So here we have two containers. You can see container number one, where you have carbon monoxide, and the mass is 2 kilogram, temperature is 77 Celsius, and the pressure is zero point 0.7 bar. In container number two, the gas is also carbon monoxide, but mass is 8 kilogram, temperature is 27 Celsius, and the pressure is 1.2 bar. Those two containers are initially connected with a valve, and the valve is closed. What we will do is to open the valve and wait for a while. So it's gonna reach a new equilibrium, meaning the temperature will be the same everywhere, the pressure will be the same everywhere. And then the problem said we can treat carbon monoxide as ideal gas. If you see that, that means you can use ideal gas equation. Okay, after mixing, we tell you the final temperature TF is 42 Celsius. And also we tell you the gas constant R for carbon monoxide is 273 joule per kilogram per Kelvin. What we're looking for is first, final pressure PF in Pascal. Second, heat transfer Q, either to or from the combined 1 and 2 system. Assume CV of carbon monoxide is constant and the value is given as 0.745 kilojoule per kilogram per Kelvin. Okay, so let's start from part 1. Look for the final pressure. How do we look for pressure and which equation has pressure? Yes, that's correct. Ideal gas equation. Okay, so we're gonna choose this one. P times nu equal to RT. There are many different formats in ideal gas equation, and you can choose any of them. This one is probably easier. P nu equal to RT. Okay, so since we're looking for a final pressure, so we will apply this ideal gas equation to the final state, meaning we're gonna add the subscript F final to every parameter in this equation except R. Why? Because R is gas constant. It doesn't change, so it doesn't need a subscript. Okay, because we're looking for the final pressure, so what we do is to move PF, the final pressure, to the left-hand side, and everything else to the right-hand side. This equation becomes R times final temperature TF divided by final specific volume nu F. Okay, let's take a look. Do we have everything in the right-hand side? R, yes, given. Final temperature TF, yes, given. Nu F, final specific volume, we don't have it. So this question goes down to look for nu F, final specific volume. How do we look for specific volume? We probably want to go back to the definition of specific volume. The definition of specific volume is volume over mass. Since we're looking for the final specific volume, we add a subscript F, meaning final to every parameter. Okay, so now let's take a look. What is the final volume? Final volume is the combination of V1, the volume of container number 1, and V2, the volume of container number 2. Because you've opened the valve, everything mixes up. So the final volume is V1 plus V2. And the final mass, similarly, it will be M1 plus M2. Mass of the carbon monoxide in container number 1 plus the mass of carbon monoxide in container number 2. Okay, so now let's take a look. M1, M2 are already given. Volume V1, volume V2 are not given. So we need to find V1 and V2. How do we look for volume? Which equation has volume that we can use? Exactly. Ideal gas equation again. Okay, so what we're gonna do is, let's recall right here. Recall PV is equal to MRT. This is another format of ideal gas equation where V is volume. So from this equation, we can find volume. Volume is equal to mRT over pressure. So now we can go back and rewrite V1 and V2 with this equation. V1 will be rewritten to M1 R T1 over P1, and then V2 will be rewritten to M2 R T2 over P2. And again, R doesn't need a subscript because R is gas constant, it doesn't change. Okay, and then copy the denominator, which is M1 plus M2. So now that let's take a look. Do we have everything in the right hand side? M1 given, R constant, T1 given, P1 given, M2 given, R given, T2 given, P2 given, M1 given, M2 given. So now we have everything in the right hand side. What we need to do is to plug in everything. M1 is 2 kilogram, 2 kilogram. Double check is SI unit. Multiplied by R. What is the R for carbon monoxide? It's given as 273. And the unit is joules per kilogram per Kelvin, so that's SI unit 2, 273. Multiply by T1. What is T1? Let's go back. T1 is given as 77 Celsius. So what you need to do here is to make sure you use Kelvin because Kelvin is SI unit for temperature. Okay, so we have 77 Celsius. We need to convert it to Kelvin by adding 273. Okay, and then divided by P1. What is P1? Pressure P1 is given, which is 0.7 bar. And again, we need to convert bar to Pascal. 0.7 bar, 1 bar is equal to 10 to the 5th Pascal. So multiply by 10 to the 5th. Okay, so that's the first term in the numerator. Second term in the numerator, we just repeat. M2 is 8 kilogram. R273. T2 is 27 Celsius converted to Kelvin by adding 273. Divided by P2. P2 is 1.2 bar converted to Pascal by multiplying 10 to the 5th. Okay, and then divided by the denominator M1, 2 kilogram plus M2, 8 kilogram. Alright, so the final solution for nu F is 0.819. And what should be the unit? The unit must be SI because I used SI unit for everything in the right hand side. So the unit must be cubic meter per kilogram. So now we found nu F. Then we can go back to this equation, take a look again. Do we have everything in the right hand side? Yes, so now we can easily find final pressure. PF is equal to R times TF over nu F. R is equal to 273, giving SI unit. Final temperature is 42 Celsius. Make sure you convert it to Kelvin. And then divided by nu F, 0.819 SI unit. So the solution for final pressure is 105000. And the unit must be SI. So it's going to be Pascal. Okay, so this is part one, how to look for the final pressure by using ideal gas equation. Okay, and now let's go to part two. What is part two? Part two is to look for heat transfer Q and the direction. It's either going into the system or coming out of the system. And also we tell you CV of carbon monoxide is constant. The value is given. And pay attention to the unit because kilojoule is not SI. Okay, which equation can you think of to look for heat transfer? At this moment, we only have one option, that is first law of thermodynamics, which is Q minus W equal to delta E, we learned earlier in this class. Okay, and recall, we do have a requirement you have to satisfy before you apply this equation. That is, the system must be a closed system. So now take a look. Our system is the combined container number 1 and number 2. So do you see any inlet or outlet for this combined system? There's no inlet or outlet for this combined system. So yes, this combined system is a closed system. And yes, we can use the first law. Okay, so now we look for part 2, heat transfer. And like we said, we're going to use first law. Q minus W equal to delta E. Q is heat transfer, W is work, and delta E is the change of total energy. Just like before, delta E has three components. They are delta KE, delta PE, and delta U. Kinetic energy, potential energy, and internal energy. Okay, let's take a look. Is there any term that we can cancel? Delta KE. What is the change of the kinetic energy? What is the initial velocity of the gas? 0. What is the final velocity of the gas? 0. So there's no change of kinetic energy. What is the change of potential energy? Is there a change in height? There's no change in height, so there's no change in potential energy either. And then there's one last term that is 0. Which one is that? Do we have work? Does the gas generate work or consume work? In other words, does the gas push something, such as a piston, or does the gas get pushed by something, such as a piston? No, there's no moving parts in this question, so there's no work involved. So work goes to 0. The system doesn't generate work or consume work. So this equation becomes Q is equal to delta U. And then delta means change. We always use final. So UF minus initial, UI. F means final, I means initial. Okay, let's continue. And let's recall what is capital U. Capital U is equal to mass times lowercase u, specific internal energy. So we can rewrite capital UF into final mass multiplied by lowercase uf minus capital UI initial. So be careful. For the initial state, 1 and 2, they are separated. So you need two terms. One term for container number 1 and the second term for container number 2. So for container number 1, it will be M1 U1. For container number 2, it will be M2 U2. Okay, so now let's take a look. Do we have M1? Yes, 2 kilogram. Do we have M2? Yes, 8 kilogram. So what is final kilogram? 2 plus 8, 10 kilogram. So we have the three masses very easily. And then this question goes down to looking for specific internal energy, UF, U1, and U2. Okay, like we said earlier in this class, you can either go to the tables to look for U, or if you have ideal gas, you can use the equation, which is U is equal to CV times T. You can use this equation to calculate specific internal energy, lowercase u, if CV is a constant, and CV is a constant because the problem said so. All right, so this question becomes Q equal to MF. Now we rewrite UF with this equation. It becomes CV times TF. Then we do the same thing for U1 and U2. It becomes M1 times CV times T1, and this becomes M2 CV times T2. Okay, so now what do you notice? Every term has CV in it. So what we can do is to take CV out of it, and what is left is MF, TF, minus M1 T1 minus M2 T2. Okay, that's it. So now we have everything in the right hand side. We're just plugging all the numbers. CV, what is CV for carbon monoxide? It's given. It's given as here, 0.745 kilojoules per kilogram per Kelvin. And be careful here because kilojoule is not SI unit. So I'm going to convert kilojoule to joule by multiplying 1000. Okay, so now it's SI unit. Okay, multiplied by MF, final mass, like we said, is 10 kilogram. What is final temperature? Final temperature is given, which is 42 Celsius. 42 Celsius. Okay, and be careful here because you have to make sure you use Kelvin. Minus M1, M1 is 2 kilogram, and what is T1? T1 is 77 Celsius, converted to Kelvin. Minus M2, M2 is 8 kilogram, and T2 is 27 Celsius, and again, converted to Kelvin. So now, solution is 37.25 times 10 to the third. This is the solution. And what will be the unit to the solution? Because I used SI unit for everything in the right hand side, so your solution must be in SI unit. What is the SI unit for heat transfer? It is joule. Okay, and then we can do one more step to convert it to kilojoule, because kilojoule is usually the unit for engineers to use. Okay, so now this is our solution for heat transfer, 37.25 kilojoule. And don't forget, there's one more question. What is the direction of heat transfer? Is it going into the system or leaving the system? How do you tell? You can easily tell from the solution itself. Because our Q is positive, what does that mean? If the heat transfer Q is positive, that means your system gains heat. So that means heat is going into the system. If heat transfer is negative, that means system loses heat. So the heat is leaving the system. In this case, because Q is positive, so our system gains heat. Heat is going into the system.